this problem, we're asked to find the volumetric flow rate into the pipe, and we can use this by setting Q dot in equal to Q dot out. This is true because of the conservation of mass. All the mass coming into the system is going to have to exit it. And we're giving all the information necessary to find what Q dot out is. And so if you run through right here, shows the calculations needed to find what Q dot out is, and relating that back to Q dot in, we can find that Q dot in is equal to 0.01 meters cubed per second. Okay, so the next part of the question is a little bit more challenging. We need to find the reaction forces required to keep this piece in place with the flow rate coming in and the flow rate coming out. And so to do that, this is the equation that I used. It's a simplification of the Reynolds transport theorem, and it basically relates, or it's a conservation of linear momentum. And so since momentum is going to be in all three directions, I hat, j hat, and k hat, I represented everything with vectors. And this is all the sets of equations that I use to calculate what is going on. And so it is kind of a lot to run through in a 2-minute video, but in a sense, you have the momentum forces, or the reaction forces that need to counteract the momentum from, let's see, going just to the problem statement, from the velocity profile coming in and the velocity profile coming out. And then you also need to account for the pressure on the inlet, and that's going to be in our forces external. There's no pressure on the outlet because the outlet is exposed to atmospheric pressure, and that means that there's no force built up by that. And so if you go through and you calculate what this is the mass rate of change, and then this is the vector value of velocity. You go through and you calculate what all those quantities are for the flow rate coming in and the flow rate going out. You end up with an equation that simplifies down to this, which is the reaction forces needed to hold this piece in place. And in order to solve both these problems, we needed to make the assumption that there's steady flow for the second part, and that the density of the water is constant at 1,000 kilograms per meter cubed. Okay, thank you for watching my presentation.